Hello everybody, my name is Mehrdad Hajizadeh from Technical University of Chemnitz, Germany. And along with my colleagues Sudi Barua and Pega Golchin, we wanted to actually present our work, which is so-called FSA-IDS, a flow-based self-active intrusion detection system. The first question would be then, what is the intrusion detection system? It's a crucial component in the network where it can take a copy of the traffic to check for the malicious activity. And if something is happening, it actually generates some alert so the security team can actually do the proper action against that attacks or malicious activity. We have different kind of intrusion detection systems like signature based, which is rely on the detecting known attack. It has a signature, and you can see here Snort is one of the famous product of signature based IDS. So if the attack traffic come to the network and it's matched with the database, it's produce the alerts. And it's explainable approach because it can say what happened, who did this, how, when, and where. But if the attacker changed the malware behavior or attack or update or create a new attack, which is not matched with any signature here, it can bypass and infect our internal network, as you can see. So then we can summarize the limitation of the signature base, which is relies on a signature database, detects only known attacks but fail to detect unknown, and it requires domain expert involvement as it should generate some signature and update the current signature database. And it can be failed to detect among encrypted data because most of the signature base the IDS use deep packet inspection and look for the payload of the packet, which is now encrypted in most of the communication. Then we go for the second type of anomaly-based IDS, which is instead of relying on the predefined signature, we try to use some techniques to learn the behavior of the normal traffic in order to classify the abnormal activity in the network. And of course, one of the famous way to do this is to use machine learning, where it can learn underlying characteristic of the network traffic. So the main advantage would be to detect known and unknown attacks. So one of the famous approach is to use supervised learning. So where we actually uh, create some data. In this case, we use traffic flow statistics like number of packet bytes, maximum packet size, and so on and so forth, but not the payload information with the label for benign and malicious into the model, and then we train the model with this data and hoping to detect some malicious activity. However, it also has some actually limitation. The first limitation is that it's required availability of both benign and malicious labeled data for training and evaluating. So which is not very realistic in real production. And some of the supervised learning like neural network is the data hungry and they require a massive number of labeled data to train. On the other hand, data labeling is costly, complex, required massive human effort, and might be impossible in some special cases, for example, for privacy issues. So, what we should do to train this model? Maybe you should say, okay, we can use unsupervised learning, which does not need label data for training. So we are just feeding the model with the data without label and hoping that it can detect the malicious activity. However, we're also facing with some limitation with unsupervised learning, which they are famous for high false alarm generation. So then the second thing would be the explainability of unsupervised algorithm in the lack of label. So how the algorithm decide to consider this sample is normal or abnormal. The explainability is difficult in the case of unsupervised learning. And the last one is that okay, we have, for example, in clustering tests, we have some cluster but we don't know which cluster is normal, which cluster is abnormal. So still we need to engage a domain expert, and we require some label and visualization techniques to consider what are the outcome of this. So the interpretability of the result would be difficult. So then in this slide, I will actually explain the challenges regarding the lack of label data. We need the label data because we need the model to be continuously updating for different reasons. For example, for concept drift, where the traffic characteristic of the traffic is changed over the time, then the initial trained model would not actually have a good performance regarding these changes, or in adversarial machine learning. So we need to retrain a model. So retraining requires the label, and without label, it's a very complex and challenging task to do this. On the other hand, we have explainability of unsupervised learning from interpretability and result assessment that we spoke in the previous slide. And if we don't have label data, it means that we are increasing the domain expert involvement in the process of machine learning. So we reduce the automation. So because we need the data labeling, we need a much expert for data labeling, for effective model deployment and validation. Those challenges actually motivated us to propose and building an effective ML-based IDS which required a limited available label samples. And it reduced the domain expert involvement through a smart labeling and automation. So the question is that can we use an ML model for labeling to reduce domain expert involvement? The answer is yes. We can use semi-supervised learning, which has some different techniques, and one of them is self-learning, where we use an ML model for labeling. In this case, we initially train supervised model with the available small label data set, and then we use that model to predict over the unlabeled data. So then based on some criteria, we accept some of those labels, which is so-called pseudo-labeling. After pseudo-labeling the unlabeled data, we retrain the model. So then the pipeline is going to be a start with putting some unlabeled network traffic, then do some flow information extraction, for example, the number of bytes, number of the maximum packet size, and so on and so forth. And we do some data pre-processing before we feed the data to the machine learning model. And here we have not only one but different kind of supervised, initially trained supervised model in an ensemble setting, and these supervised settings actually do the prediction over this unlabeled data. So then if it can fulfill some criteria or threshold that we define, we accept that label, and we put that label to the label dataset, and we retrain the model. That this part is so-called self-learning. So the criteria is based on the confidence of the machine learning model about label prediction. If it is high confidence, we consider this label and put it to this. But in the self-learning, the low confidence, which model has the most uncertainty about those sample, will be ignored, which is the issue that we are facing. But in reality, these low confidence are the informative sample for the machine learning to be improved, and we should not ignore them. That's why we use active learning to query those actually informative sample from the human expert. So we take back the human expert into the loop. So we have the human in the loop here. So the human only label those uncertain sample, not all the sample. So then uncertain sample come to the human, and it's actually do this labeling on that, and then we add it to this. But the thing is that we, of course, reduce the number of labeling effort through this uncertainty sampling because we are not doing this for all unlabeled data. But the question is that can we actually further reduce the number of query to the domain expert? The answer is yes, and this is our second actually contribution where we're using the clustering assumption. The cluster assumption says that two sample in a one cluster uh, has similar or identical label. So before we put the we asked and query those uncertain sample from human expert, we are cluster them to different cluster and we just choose some of those uh, candidate sample from each cluster and we just query those candidates. When the human expert actually uh, when the human expert label those, we propagate those label to each corresponding cluster. This way, we not only actually reduce dramatically the number of queries to the human, we also speed up the labeling procedure, and we have more labels here coming to this label data set. But we have different challenges here. The first challenges it would be that how we can do the clustering without involving the human expert, because most of the clustering approach require to set the number of cluster before clustering, but here we use the state of the art clustering approach, so called HDB scan, where it does not require to set the clustering number of cluster before feeding the model. And it is also provide us a soft clustering probability where we can use in order to consider a set of candidate based on those criteria. But the main problem here is that what if we select some candidate from each cluster and label it by human, but we found out, okay, after labeling there are some contradiction. So which label we should actually propagate? This is the main challenge that we should actually handle in this model. So this is the next contribution that we did for to handle this situation, where we proposed label propagation conflict resolution strategies. We proposed two actually strategies, the homogeneity based and the majority based. In a homogeneity based, if we found a contradiction between labels after human labeling, after human annotation, we only consider the contradiction up to the 10%. If more than 10% actually contradiction found, we query the whole cluster. And then we do the label propagation as before. The advantages is that we provide a high quality labeling. But the disadvantage is that in the worst case scenario, we need to query all the samples in the cluster. On the other hand, we have a majority base. In a majority base, we apply the majority rule for label propagation, and for example here the benign is the majority, so we propagate the benign into the cluster. The advantages is that we have less queries as we relax the threshold, but the disadvantages would be that we might actually have some erroneous propagation. So this is the complete proposed FSA-IDS framework, as you can see. Then it combined the self-learning and active learning, as well as adding the clustering in order to increase the automation and reduce the number of queries to the human. If we want to go to the experiment overview, we use two real-world datasets, CTU13, which is a labeled dataset with 7 different types of malware traffic in different scenarios, and it also provides a benign traffic. And also we use CIC-IDS 2017, which also labeled and provide benign, DOS, brute force scan, infiltration, botnet, and so on and so forth. We have two groups of baseline, the supervised model, which is random forest, k-nearest neighbor, and convolutional neural network, as well as non-supervised model, which is isolation forest, local outlier factor. For performance metric, we have two groups. The first regarding the detection performance with precision, recall, and F1 score, and the second is the data labeling performance. What is the quality of data labeling? We have different metrics like number of queries, label propagation impact, and pseudo labeling quality. Then we have the prediction performance. As you can see, the FSA-IDS majority and homogeneity are the two last, and they are initially trained with only 500 sample. But in the supervised setting, we trained the model with 100,000 to 120,000 sample. So, but we still can get the similar accuracy like the supervised learning. And in comparison with the non-supervised learning, we got much better actually accuracy in comparison. It can be also be highlighted here that you can see that the non-supervised generate a lot of false alarms, and the accuracy is super low compared with our works. We also compare our metrics with some recent work in the same data sets. For example, in CTU13 we got 93, which is more than the rest, and in CIC-IDS we got 90%, which is in comparison, we outperformed the other similar works. And for the data labeling performance, we can see the most important parameter is the number of queries to the oracle or human. You can see that in both cases, in two different data sets, we have minimized the number of queries dramatically in comparison with other models here. And in order to know that how our pseudo labeling module works and how good it is, we use FNR and FVR. As you can see that it has a very, very low mistakes through pseudo labeling the traffic. What we can do, what we can take away from this slide. The first thing is that the label scarcity is really a major challenge for deploying ML-based IDS in a real production. And FSA-IDS is effective in terms of intrusion detection in comparison with the supervised and unsupervised model. FSA-IDS required a small number of label samples for initial deployment, and FSA-IDS reduced the labeling effort dramatically through clustering, and FSA-IDS extend the training dataset without extra cost because we're just using the machine learning itself. I would like to thank you all for your attention, and I'm happy to take any question in this regarding to this presentation.